Hello and welcome to the video for basic audio production for Monday, September 28th. I'm going to let people in from the waiting room.
What up?
I'm good. How are you?
Alive.
Which is an improvement?
Yeah, it's always an improvement.
That's excellent. Anything exciting happen for you over the weekend?
I went to work and it was really busy and I hated life.
Oh no. Man, I feel your pain. Where do you work?
I work at this thrift store over on Pantano,
Uh-huh.
called Enjoy, and I basically just work in the warehouse and you know try and organize all the donations people bring in.
Oh wow.
Yeah.
Yeah. I've seen the back rooms of places like that. There's a There's a place on Fourth Avenue that I donate stuff to. It's Goodwill, I think. And uh, man, those warehouses in the back
Hey,
are
Greg.
crazy. Hi, Carl. How you doing today?
Uh, it's not a good day, but I'm here.
Okay. Well, we're glad you're here. Um, yeah, Vlad, I totally feel your pain. Now, do you get a lot of good stuff in that donated to you guys?
So some of it's good, but I think other people think thrift stores are landfills because we get a lot of trash too.
Yeah,
We're
that's funny. That's funny. I know it's really hard to figure it out, like what people can actually use, to donate to thrift stores. Cool. Well, all right. Well, welcome all you guys. Let me go ahead and just put you in the attendance real quick. Okay. Just logging into the Pima attendance right now. Okay. Let's see. So basic audio production. All right. Okay. Where's the class? Right here. Okay. Let me open up the chat. Okay, cool. Hey, well, good morning and welcome to the audio class. We're gonna look at some cool things today. I've got a really nice video. It's only 5 minutes long, but the gentleman in it does a really nice demo of how to use a boom pole. And he gives you some professional tips, and it's really well done. So we're going to take a look at that. Also, we're going to go over. I told you guys we're going to have a quiz on, mics and other sound definitions of things that we've talked about already this semester. And I decided to make the test open book, the quiz open book, because it's a lot of information. And what I really want you guys to do is just, read these questions, go find the answers, write them down, and in that process, kind of, reaffirm the learning of what these different things are. Like what is, for example, what is a dynamic microphone, and when would you use that? So, that's the purpose of this little quiz, and I made it open book so it's easy for you guys, hopefully, and you guys can retain some of this information moving forward into your careers. So let me switch over to the class website here. Let's see. Pima. Dreamco.com, and then basic audio production. Okay. So before we get started up, is there anybody who has a project one that we haven't seen yet? I know sometimes some people turn in projects late. So if you've got a project one we haven't seen yet, let me know and we'll pop on over into your folder and check it out. Okay, the next thing is that we're going to watch this video about how to use a boom pole. So let me go ahead and share my screen. Okay, and you guys should see that now. And let me go ahead and click on this video. And like I said, it's only 5 minutes long, but it's well worth watching. The guy does a really good job. Oof, I'm clicking on it. Okay.
If you want to produce a great video, you're going to need great sounding audio along with your picture. In this video, we'll show you some insider tips from professional boom operators. Since the advent of the first talking pictures, filmmakers have relied upon mounting a microphone onto a boom pole in order to position the mic overhead of the actors and just out of frame. This gets the microphone closer to the actors than leaving it on top of the camera. It also angles the mic so that ambient noise striking the sides tends to be rejected while actual dialogue is in the pickup zone. Always use a good shock mount to isolate any handling noise from the boom pole. Don't just insert the mic into the center opening of this tic-tac-toe grid. You always want to crisscross or over under the horizontal bands so that the mic is securely supported. After inserting the mic, connect the audio cable. If necessary, wrap the cable a half turn or a full turn around the pole so that excess cable slack won't knock against it. Professional boom operators add a small wrap of cloth camera tape where the rear of the mic plugs into the cable connector to avoid any mechanical clicking where the metal parts meet. You should also add a thin strip of camera tape to the tip of your windscreen. This makes it easier for the camera operator to see the location of the mic in the viewfinder, especially when shooting against a dark background. Here's another quick tip. To establish your working frame line with the camera operator, begin with your mic dipped completely in the frame, and then gradually raise it until it just clears the viewfinder. That will get you closer to your actors than lowering the boom from way above and asking the camera person to warn you when approaching the frame. When you extend a boom pole, first you want to slide each section out as far as it will go until you feel the stop. Then, back it in a couple of inches before you tighten it down. This is important so that each section has a little bit of overlap and gets supported in two places: the end of the inner tubing as well as the locking collar of the outer pole. Only tighten down the pole finger tight. Otherwise, it will take a lot of awkward straining to re-loosen when you need to adjust length. Hold the boom pole completely over your head so the mic dips down ever so slightly. Keep the front arm vertical, elbow locked and tucked close to your head. This is the supporting arm. In this position, it's easy to bench press a couple of pounds. If your front arm goes horizontal, then the pole will feel a lot heavier. The rear arm is the steering and control arm. Use it to tilt and swing the pole. You can also move both arms together in order to make the boom pole reach in or back out. Rotate the pole with your fingertips in order to aim or cue the mic from actor to actor. As much as possible, aim the mic towards the actor's nose. You want to come in at a slight angle, somewhere between 45 and 90 degrees. If there are two or more actors in a scene, then you may need to move your pole so that you can alternate from actor to actor, or at least find one position that allows you to cover both of them equally well. It really helps if the boom operator can hear the soundtrack on headphones. There are special duplex cables for this purpose, but you could do it with a simple Y-splitter and a headphone extension cable. Higher quality condenser shotgun mics, such as the BP4073, offer a very smooth transition between their on-axis response and their off-axis side response. Referred to as being flat off-axis, it means that audio from the off angle will still sound good, just at a lower volume. Sound mixers and their boom operators often take advantage of this if they have to balance two actors who speak at different volumes. By placing the louder actor slightly off-axis, it brings his volume down compared to the actor who remains centered under the mic. The background sound in the scene, what we call room tone, remains constant because we do not have to alternately raise or lower our recording volume. Holding up a boom pole can get tiring after a while. Here are some tips to make it easier. Extend your boom pole to almost its maximum length, and then move your grip closer to the center so the pole is better balanced and not so front heavy.
Now you're only bench pressing a couple of pounds instead of finding leverage and torque that would work your muscles. If you have to boom a really long scene, grab an unused stand and use it as a support. Here's the secret. Don't use the stand to directly rest the boom pole. Use it to rest your elbow and to take the strain off your supporting arm. You can use a small pillow or sandbag as a pad. That way, the pole is still gently held and controlled by the fingers, and moving the boom pole on and off the stand will not produce an audible clunk. With these simple tricks, you can boom like a pro. In the video studio or on location, Audio Technica has you covered.
Okay, so boom pole. What did you guys think? Did you like that video?
Yee.
Yeah, it's pretty good, huh? Um, so, obviously some of the key things there, he talked a lot about techniques and some of the things I thought were really very important were like putting the cloth tape around the connection between where you plug the XLR cable into the microphone. That's really important because those things do move around. I like the idea of putting the tape on the end of the windscreen so you can see the pole. And then he had a lot of really good ideas about how to balance that so you don't get tired. And then of course the Y splitter cable. You've got your audio coming from the boom pole. You can put that into what's called a Y splitter because it's called a Y because you get one signal in and then it splits off into two, like a Y. And one of the signals could go to the camera operator and the other could go to you with a pair of headphones on. And of course, you'd be a lot better off hearing the actual sound you're recording because then you can tell if you're getting extra sounds or if it's not loud enough or any of those things. So those are some really key points that he made in there. Okay, and that video is there for you guys to check his references if you ever need to, if you're doing a shoot. Of course, in your other classes, in your film classes with Loomis, he'll go back over this information, but I want to make sure that you were exposed to it and at least knew the basics of a boom pole operation. Okay, so I'm going to switch back over to the class website. Let's see, I think I can probably just hit my back button. Yeah. Okay, so the main thing we're going to do today is go over these terms that are going to be on the open book quiz on Wednesday. And you're probably your best bet would be to have some kind of note-taking gear available right now. Whether you're just typing into a little document on your computer or writing notes in a notebook or something like that. Basically, the notes that you take today can be used as the answers on the quiz. You just have to, basically fill in the blanks. And the questions and answers I'm going to give today are going to be the same ones they're going to be on Wednesday. So the first thing we're going to do is we're going to define something called a sound envelope. And let me go ahead and click on this menu here. So it says in sound and music, let me make this a little smaller so we can see it. Oh wow, I'll just have to make my whole website smaller like this, and then I'll make it bigger again so we can read it. Okay, it says in sound and music, an envelope describes how a sound changes over time. So that's actually as far as I want to go in the definition of it. So a sound envelope is how a sound changes over time. Now, the sound that I like to think of is something like a synthesizer, a synthesized sound, because that gives a really good example of these four principles of a sound envelope. So it says the most common kind of, so when a synthesizer creates sound, it creates sound via something called an envelope generator. And an envelope generator is like, a bunch of electronics that figure out how it's going to generate a sound. And because it's a computer, you need to tell everything about the sound. So, what the engineers have done is they've taken a sound and they've broken it apart into four distinct areas. The first is called the attack. And the attack is the beginning of the sound, right? It's like, does the sound immediately start or does it, kind of ramp up slowly? And I'm going to play some examples of this in a second. So the first part is the attack. And you can see from this little example over here, like let's say that this little gray line is a sound wave, right? Or representative of a sound. So the first part of the sound is the attack, how it, starts. After that initial attack of the sound starts, quiets down a little bit. Maybe the attack's very loud and it quiets down a little bit. That second phase here is called the decay. And that's, the sound kind of coming down from its peak attack to sort of a more consistent sound level. That consistent sound level that goes to is called a sustain. And that's represented by this sort of regular line. It's like a plateau. And then finally, when the sound is dying off, that's called the release. So, I think that this little graph here is very useful. If you think of a sound like, going bong, like that, it starts off fast and then gets a little quieter and goes, right? A steady sustain, and then going from the sustain to quieter, right? Just kind of disappearing, right? So that's the definition of these four aspects of sound. And now I'm going to play you actual sounds that correspond to those. So once again, here is the little grid, the little map that we saw. And here are some examples. So it says the attack is the portion of the sound envelope that represents the time taken for the amplitude to reach its maximum level. In other words, boom, it's going to go up to its highest peak right at the beginning. And this is really loud, actually, so I got to go really quiet. Let me play this. Okay, that's not too bad, so I can turn it up a little bit. So what you'll hear is a little synthesized sound starting out and then moving up to a higher volume. That's the attack, right? It's that, you can listen to the sound and then look at the chart too, and you can get the visual of the sound going up, right? Now, we have the decay. And the decay is the progressive reduction in amplitude, and amplitude is how high a sound can get, right? Of a sound over time. Okay, so let's listen to decay. So you hear the sound being a little louder at first, and then it gets quieter. So it comes down a little bit. So we've got our attack, and then decay, right? Now, every sound is held for a certain amount of time, and that's referred to as the sustain, and that's when you get the sort of the consistent volume of the sound. And so this is sustain right here, right? And then finally, the sound disappears, eventually fades out, and that's the release. So you can hear it release. Okay, so I'll play all four of these one after another. So attack, decay, sustain, release, right? Once again, this little graph right here. Play one right after the other. Now, granted, those are pretty subtle variations in the sound, and you'd have to be listening really closely to hear, oh, this one's going up, this one's going down, this one's sustaining. But it's more the concept. It's more the fact that really this is just a principle. It's a physical principle of all sound. It starts out, it gets a little quieter until it reaches its consistent level, and then it eventually fades out. So that's called the sound envelope. It's a way to characterize all the different elements of a sound. Okay, so, and that will be on the open book quiz, and we'll talk about that in just a sec. And that was the one thing that I didn't get a chance to go over with you before this week, so that's why I wanted to mention that. So now let's go on to talking about the quiz and the information that's on it. There's 10 sections here, and they just talk about things that we've talked about, over the period of 5 or 6 weeks. And it's information that will be helpful to you to understand how audio works. So I'm going to switch over here. These are the questions here, but I'm going to switch over here to my notes, which also have the answers on, right? So we'll go here and talk about the questions and the answers, right? So the first question is, what is the difference between dynamic, condenser, and ribbon microphones? Let me let somebody into the class here real quick. What is the difference between dynamic, condenser, and ribbon microphones? So I've got my little book here. And the difference between these type of microphones is in the way that they pick up sound and also how expensive they are to buy and what they're used for, right? So for example, oh, here's another person who wants to come in. Okay. So let's see, he's joining. Okay. So let's start by talking about the dynamic microphone. So you guys remember me showing you this microphone right here, the Shure SM57, the round head microphone. That's a dynamic microphone. They're inexpensive. They're very hardy. They can take a licking and keep on ticking. And the way that they work, the way that a dynamic microphone works is all microphones work with a diaphragm, which is some sort of material that get hits by the sound and vibrates. And then there's different ways that those vibrations are transmitted into electrical energy that's then recorded as audio, right? In the case of a dynamic mic, what you have is you have a stiff mylar diaphragm, so sort of a stiff plasticky kind of diaphragm, which is attached to a finely wrapped coil of wire. And that whole thing, the wire and the diaphragm, are suspended in the middle of a magnetic field, okay? Here's the graphic right here. So you can see that that little sort of coily, wiry thing is the wire. The diaphragm's on the front, and then the top and the bottom gray areas are the magnets, right? So what happens is you have a magnetic field which has sort of a constant rate of electricity, right? And then you have this diaphragm with a little coil in it. Well, what happens is when sound hits the diaphragm, it vibrates, forcing that coil to move, and the coil displaces the magnetic field. So it changes the magnetic field, generating electrical current. And the electrical current it generates is exactly equal to the amount of vibrations that it does. So in other words, it's making an exact replica of the sound, but it's transcoding it over into electricity from acoustic sound pressure, right? And that's what your computer records. It records those electrical signals, and there's a little translator in there that turns it into audio, right? Okay, so that is how a dynamic mic works. I have written down here, a stiff mylar diaphragm is attached to a finely wrapped cord of wire. It's suspended within a magnetic field. When sound hits the diaphragm, the voice coil moves. That coil of wire is called the voice coil in the magnetic field and produces an electrical signal that is recorded as the audio. Okay, so that's how a dynamic microphone works. Now the other two microphones are much more expensive and are used for finer purposes. I'm going to skip down here to the ribbon microphone because the ribbon microphone works the same way as the dynamic microphone. But instead of like a stiff mylar diaphragm, what it has is it has a very thin ribbon of aluminum. And in fact, let's see. This little, you see that little center corrugated piece of metal in the middle of this picture? That is the ribbon of a ribbon microphone. And it's extremely sensitive. And once again, it's suspended in a magnetic field. So as it gets hit with sound pressure, which is the audio that we generate, it vibrates, displaces the magnetic field, and that information is recorded as audio, right? So here's the definition of a ribbon mic. The ribbon mic works the same as the dynamic mic. It uses an extremely thin diaphragm of aluminum ribbon suspended inside a magnetic field. As sound hits it, it moves in the magnetic field, generating an electrical signal as recorded as audio. Now, ribbon microphones are expensive. They're generally not taken out of the studio unless you're doing something like recording an orchestra. And they're really good for things like, sounds like violins that have, incredible rich tones that you need to pick up all the fine subtleties of. Now, the third type of microphone that we're going to talk about here is called a condenser mic. Now, these mics are also expensive, but these are sometimes taken out in the field. Like, for example, a little down, further down, we talk about, or actually, I think it's in, number 4 here. We talk about what type of mics are used with boom poles. And generally, these are condenser mics. They're really good mics, but they're a little pricier than dynamic mics. But the way that a condenser mic works, once again, they all work with this idea of a diaphragm, but a condenser mic works in kind of a different way. What it does is it has two plates. One of them is called the back plate, and the other is a thin diaphragm. Let me show it like this. So here's the back plate, and here's the thin diaphragm at the front, right? What happens is when sound hits the diaphragm in the front, it vibrates. And what it does is it changes the amount of space between the back plate and the diaphragm when it vibrates. So here it's just neutral. Now there's less space. Now there's more space. Well, the magnetic field, that's wrapped around that measures the capacitance of that, how much room is in between those two plates. And then it changes the electrical signal based on, whether it's more room or less room. And so this is called a capacitor, something, that measures that amount of space between these two plates. Or another term for it is a condenser. And that's why this is called a condenser microphone. So the definition of, and of course, an electrical current is put, in here to power the magnetic field. And that electrical current is often generated by something called 48 volts or phantom power. And so oftentimes what you'll find is these condenser boom microphones, they need to have power sent to them from whatever is recording the audio. And so you'll see like, a little box that's recording the audio. It'll have a little field, a little channel strip, and on there will be a button that says phantom power or 48V for 48 volts. And you press that button and suddenly it's sending 48 volts of DC power to the microphone to create that magnetic field, that electrical field for the condenser so that it can record the audio. So it says condenser mic is this is the definition of a condenser mic. A regulated DC power supply is applied between one fixed backplate and a movable diaphragm. The two plates form a capacitor or condenser, which gives the mic its name. When sound hits the diaphragm, it changes the amount of space between the front and back plates, and this is registered as an electrical signal that is recorded as the audio. Okay, now when you're out on the street, nobody's going to come up to you and say, define a condenser microphone, right? But when you're working inside of, the film industry or whatever industry you choose to go to, it's important to know how these things work, the fact that many condenser mics need phantom power, because if you try to record something without the phantom power turned on, you're going to be like, what's wrong? This microphone's broken. And if you understand how it works, it makes it a little easier to use the item. Okay, and then this is what I talked about a little bit before. Which of these are expensive, which are cheap, and what type of microphone is generally used with a boom pole? Well, so condenser and ribbon microphones are generally more expensive because they're finer quality and they record more subtle sounds and a wider range of sounds. And the dynamic microphones are cheaper, and they're used for multi-purpose. And like I said, boom poles generally use condenser mics. Okay, so the next section here is, and by the way, if you have a question or you want to add something to what we're talking about, feel free to chime in. Max, yeah, of course you can record the class. I am recording it, and I'll put the recording on the website after I'm done. Okay, it says, what does on and off axis mean in regard to a mic? Do any of you guys know the answer to that already? On and off axis? Okay. If you're directly facing a microphone, you are on axis. Let me grab a microphone here real quick so I can demo this for you. Okay, so what I have here is a condenser microphone. The brand is Neumann. I don't know if you guys can see that. Neumann is a world famous type of microphone that was made in Germany, and they're just revered microphones. The Neumann microphones that they made in the 1960s, that people paid like $1,000 for. Of course, back in the 60s, that was a lot of money. Still a lot of money. Now they're worth, $40,000. In other words, these microphones are so good and they've lasted like, 50 years. and people still want to buy them. They still want to get the sound of these Neumann microphones. But today you can buy, their latest version of their microphones, and they're greatly reduced in price, and they have a whole variety of them. I believe this microphone was $750. Still a lot for a microphone, but it's a really nice vocal microphone. Anyway, you can see the front of this microphone is, this part right here that has the little logo on it. And so if I were to sing into this microphone, I would sing into this part of it, right? And that's what's referred to as on axis, when you're singing directly at the diaphragm of the microphone. In other words, using the microphone the way it was meant to be used, right? Singing directly into the diaphragm, on axis. If you tried to sing into the side of the microphone where this little metal band is, it wouldn't pick up very much of your voice. In fact, the only part of your voice that would pick up is whatever is bouncing off the wall and coming back into the diaphragm. This is what's referred to as off axis, which means the microphone is meant to record this way and you're going this way. So you're basically using it wrong. Now, I say you're using it wrong, but who knows? Maybe the way that you're recording your film, you want it off axis because you want something to sound distant. But you have to know the difference between the two so you can use the microphone correctly. Okay, so on axis means the subject being recorded is in front of the microphone's diaphragm. Off axis means the subject is off to the side, or even potentially behind the diaphragm. So if the diaphragm is here and I'm back here, saying stuff, I'm not getting the recording that I want, not getting the volume that I want. Okay, what is the proximity effect? Do you guys remember the proximity effect? We looked at that the other day. What is the proximity effect? Anybody? I can ask somebody. Let's see.
Makes a deeper voice if it's too close and stuff like that.
Right, very good. So when you have a microphone, as you get closer to the microphone, the volume increases. That makes sense, right? But also the bass response increases. In other words, you get a lot bassier, lower sounding tones get picked up. So that's why DJs sound the way they do with those very present, deep voices. Okay, so it says when a voice gets louder and lower as it gets closer to a mic. Okay, what is the name of the cable that is used for recording microphones, for plugging into microphones? Let me go ahead and bring up a picture of that. Let's see. XLR cable. Okay, this is the cable right here. It's called an XLR cable. It's the 3-pin cable there. It's got the male and the female connectors at the end. And that's used for plugging into microphones. Now, does anybody know whether that's a balanced or an unbalanced cable?
Balance.
It's balanced, and what does balanced mean?
Isn't it that it uses like 2 specific wires in it to make sure that the signals don't get like crossed or mixed up?
Yeah, exactly. What it does is it uses 2 wires, and what it's doing is it's basically one wire is used to cancel out any of the noise on the other wire, so that what you end up getting is just the signal itself and not any like radio waves or static or anything that got picked up by the cable. Because when you think about it, a cable, which is like metal wires inside some sort of rubber tubing or whatever, it's kind of like an antenna in a way. You stretch that thing out and, it's ready to pick up all kinds of frequencies and radio waves and everything. So a balanced cable will, take the signal and split it into 2 wires, and we'll use one signal to basically delete the noise and the extra grit and dirt out of the other wire. So what you end up with at the end is what you want to record. Okay, so that is a balanced cable, and that's used for recording audio through microphones. Let's see. Okay. What type of cable is used for electrical instruments like electric guitars? What's that cable called? It has multiple names. Any musicians in here?
Is that a TRS cable?
Yep, it's a TRS. What does TRS stand for?
Let's see. Tip, ring, and sleeve.
Correct. Tip, ring, and sleeve, and I'll show you a picture of that.
Yeah. And for the ones that are combo of microphone and speaker, that's TRRS.
Okay.
That's the phone type. And so if you're going to use your phone to record, you need a TRS to TRRS adapter
Okay.
to get the mic into your phone.
Okay, cool. Thank you, Bill. I appreciate that. So here's a TRS cable. TRS stands for tip, ring, and sleeve. And what there is there's 3 wires going to there. One goes to the tip of the cable, one or the tip of the the plug here. One goes to the ring, which is this area right here, and one goes to the sleeve. And they're all used, one's for grounding, and they're used for recording the signal. Now, does anybody know, is a TRS cable balanced or unbalanced? Well,
Unbalanced.
very good. And what does an unbalanced mean? What does it mean? Is it going to is it going to pick up noise?
I mean, it just has a single wire in it.
So yeah, it's got a single wire in it, which means it's going to pick up noise. So balanced is good. It means that the 2 wires are used to eliminate noise. Unbalanced is not good because it means that you got a single wire which can pick up radio frequencies and interference. So as a result, and I don't know what the answer is as to why they even made unbalanced cables, but as a result, instrument cables are not usually very long. The longer they are, the greater the chance that they will pick up noise. And so you'll very rarely find like a guitar cable that's longer than 20 feet. If you find one, you could potentially be creating some problems for yourself. You can see this one right here is 15 feet. Okay, so we've got 2 kinds of cables, the XLRs, which are balanced cables, which eliminate noise, and we've got the TRS instrument cables, which are unbalanced and which can generate a little bit of noise. Now, 2 other names for the TRS cable are a 1/4-inch cable or an instrument cable. It's all the same thing. Okay, so let me do something a little different here. Let me see if I can just hide the answers for a second here and see if you guys can give me some answers. Okay, so this next question, what shape of room is a good one in which to record?
A rectangle.
Okay, a rectangle. And why? Why is a rectangle?
Because of the way the sound bounces.
Exactly, right. The rectangle, what's good about a rectangle is the sound bounces in somewhat uniform way. And because the sound reflections are somewhat uniform, that means you can try to control them, right? What are some examples of bad shapes for rooms to record in? Think of geometry. What are some of the geometric shapes that you learn about in geometry? What are some of the most basic shapes out there?
A circle.
The circle, right. So a circle is a terrible environment to record in because you cannot control the sound reflections, right? I'm looking for the little diagram I showed you once about these reflections. The circle is correct. That's one of them. What's another one? What's another basic geometric shape?
Triangle.
Exactly. A triangle would be a terrible place to record because of, once again, the reflections. And what's the third most basic sort of geometric shape?
Square.
A square, exactly. So, yeah, I can't. Oh, here they are. Let me go back up so I can see my thing here so I can show these to you. Okay. So I don't know if you guys remember me showing you this diagram right here, but you can see that one of the surfaces here is circular. This one is sort of the opposite. It's a circle coming into the room, right? And this is sort of representative of a square room here, or even a triangular room. But you can see from the little arrows there, let me get this as close as I can. You can see that, especially in this circular room right here, it's really well documented that the sound waves hit that sort of concave surface and bounce in all kinds of crazy directions, as they do with this sort of square or triangular room here, and as they even do with this circular room, convex room, right? But then here, look at this. This is just a flat wall, and see how the audio is bouncing in a more uniform way. So that's the way that I'm defining sort of good versus bad recording environments. So it says here, what shape of room is a good one in which to record a rectangle, and especially a rectangle where you do something like this, where in the corner of my room here, where I've got these sound absorption these foam sound absorbers in the corner of the room. And what it does is it cuts off the corners of the room from sound, and that way we have the rectangle where sound is bouncing around in sort of a uniform way, but the corners, which are unfortunately bass sounds, lower frequency sounds, tend to get trapped in corners of rooms and they don't bounce back. So by putting these sound absorbers in the corner, you stop that from happening, and you've got sort of the ideal recording environment. And now we say circles, squares, and triangles are not good, and it's due to the fact you can't control reflected sound in those type of rooms very easily. Now, continuing to talk about sound that's bouncing around rooms, there's three kinds of sound, or I would say three types of sound that can bounce around the room, and that you can treat a room to deal with three different kinds of sound. And I just got to keep closing up my answers here so you guys can try and answer it yourself, at least guess. So can anybody tell me what type of sound can move around a room? How it moves, how it gets processed in a room? So I'll give you one clue. I'll give you the first type. The first type of sound is called reflected sound, and that is sound that bounces off of a flat surface. Now there's two other ways that sound is described when it's hitting different types of surfaces.
Absorb sound?
Yes, very good. So absorbed sound is sound that hits a piece of foam that you've hung up on the wall, and it sucks up or absorbs a certain amount of that sound. And obviously, when you're treating a room for sound, you want to have a combination of reflected sound, so that's flat walls, and absorbed sound, which are foam panels, right? Now, there's a third type of sound that it's neither of those two, and there's a term for it that refers to sound that gets sort of cut up and redirected in a bunch of weird ways. Does anybody know what that is? Okay, so that sound is called diffracted sound. Diffraction, kind of like the way that when you have a little crystal and you put light through it, how the light is diffracted and cut up into all these different colors, like a rainbow. So with diffracted sound, if sound hits a bunch of uneven surfaces, it is diffracted and cut up into little pieces that get sent in all different directions, right? And what I mentioned to you guys in the past was that one way to create a sort of natural diffractor in a sound environment is to put in a bookcase, because all the different size books and all the tchotchkes you've got on the bookcase will make the sound, hit those things and bounce around the room in different ways. So those are the type of, let's see, those are the three different types of sound. So it says, how do you define these three types of sound? Reflected, absorbed, and diffracted. Reflected sound bounces off a flat surface in an orderly fashion. Absorbed sound is absorbed by a surface like foam, right? And diffracted sound bounces off a surface in an unorderly fashion, so sort of chaotic, right? Then I say, how can you treat the walls of a room to deal with these types of sound reflections? Well, for reflected sound, you just need a flat wall. It's going to reflect. For absorbed sound, you need a foam panel. And for diffracted sound, you can either have a bookcase or you can custom make or buy these little diffractors that have these weird surfaces on them. Let me show you an example of one. So we'll call sound, yeah, diffuser. Diffuser is another term which means the same thing. Let's see. Okay, this is a cool one here. So check this bad boy out. So this is, it's referred to as a diffuser or diffractor. And what it is, it looks like a piece of art, right? It's just a giant mosaic of chunks of wood that are reflecting, you know, that are pointing all these different ways. Let's look at some of the close-ups, right? Now you can make these. I've been in studios where sound engineers just took, you know, a bunch of wood and cut it at different angles and glued it to a panel, tried to make it look, you know, very artistic. You know, there's a science to this too, so you could probably read, you know, books on how exactly to angle things. This is kind of nice right here, the smaller one. And you know, it's kind of cool. It's kind of weird looking in a way too, but at least it sort of has an artistic sense to it. It kind of looks like a pixelated image. In fact, if you're really artistic, you might be able to paint that so that it look like a picture, you know, a pixelated picture. But that's what a sound diffuser or diffractor does. It bounces the sound all over the room. Okay. All right, let's see what the next question is here, or the next section here. So let's see. I'm trying to close this up. Okay, now there's a couple terms here that I've bandied around a few times when we've been speaking, and I want to define them and tell you how they're used, right? First, I'll ask to see if anybody knows what they are. So, does anyone know what a decibel is?
Isn't that how like sound is measured?
That's exactly right. That's how sound is measured. Now, the term decibel is actually a nod to Alexander Graham Bell, who, you know, invented the phone, which was, you know, the first, the telephone was the first sort of sound transmission device that we know of. And of course, if you read history, there were other people around the world inventing the same thing at a similar time, but he's the one that's well known for it. So deci means 10, and Bell is literally Alexander Graham Bell. So a decibel is it's a unit of sound measurement, you know, and it's measured in, you know, they've taken, you know, how you have measurement systems like a foot, you know, is 12 inches. Well, so a decibel is, you know, sound that's broken up into 10 different, you know, levels. So what happens is, and this is a little hard to wrap your head around at first, but it makes a little sense if you start to think about it. Whatever the current volume of something you're recording is, that's referred to as 0 decibels, okay? So 0 decibels means, okay, you know, I've got a microphone, you know, I've got the, you know, I'm recording the sound of my voice in this microphone, and I'm currently at 0 decibels. And what that means is, decibels is a relative unit of measurement. So in other words, it's relative to something else. It's always measuring the sound versus something else. So if you record your voice and you call that 0 decibels, right? If you turn the knob on your recorder up 1, what you have done is you have increased the sound enough so that you can notice it going up. And that's referred to as 1 decibel, right? So the sound is 0, the sort of, you know, average sound that you just recorded is 0 decibels. And then, you know, as you turn it up, you've added 1 decibel. Now it's louder. You add 2 decibels, it's even louder. 3 decibels, more loud, and so on and so forth. Now the same is true with turning a sound down. If you turn the knob the other way, if you go down 1 decibel, then you've noticed the sound has noticeably diminished some. So they try to create this sound system where, you know, they created decibels at these intervals of volume where people could notice. Oh, that got louder. Oh, it got louder again. Oh, it got quieter again, right? Now, there's a whole chart. Let's see, chart, let's see, decibel volume. Let's see. Yeah, decibel loudness comparison chart. So, you know, they have, let me see if I can get this pretty big here. Okay. They have set a, you know, a scale of how many decibels, how loud everything is, right? So let me see if I can find blah, 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 just a voice. I'm not finding just a voice. So I guess the closest we're going to get is a quiet office. Okay, right now I'm in what you might call a quiet office. And the sound that exists in a quiet office, people moving their chairs about, talking, moving pens, clicking on keyboards, that registers at around 40 decibels. That's, you know, the unit of measurement that they said, okay, that's about 40 dB, right? Now, as you go up into environments that are louder, it gets up into increasingly louder dBs. So soft radio music in a home would be about 70 decibels. A loud radio would be between 80 and 90, about 85, right? And then if you've got a piano fortissimo, which means a very sort of loud piano, is around 100 decibels. So if you were at a concert hall and somebody was banging on the piano, that would be 100. A full symphony orchestra goes up to 110. When you hit a hi-hat, a cymbal, you get 120. A live rack band is 130. Now notice that there's a what we call the pain threshold of decibels. So if you've ever been like listening to a stereo and somebody turns it up really loud, and you're like, ow, or you're at a rock concert and you're like, oh my God, that hurts. That means you've hit this threshold of pain, which is around 120 decibels, right? So in other words, the sound can actually hurt you, if it's loud enough. And you keep going up past that, and past 140 decibels is like the sound of a jet engine. And of course, if you stood too close to that, you'd be hurting. Which is why all the people on the tarmac, at runways are wearing the foam earplugs. Now going down very, very low here, they've set the 0 decibel at the threshold of hearing, which is just below very faint leaves rustling in a forest, right? So it's kind of amazing that we have this this whole spectrum of hearing. A human being can be out in a forest and they can hear a little chipmunk rustling around on some leaves. That's just above the threshold of hearing. That's just one of the quietest sounds we can hear, and there's some sounds slightly quieter than that, like maybe a baby just making little cooing sounds or something. And we can hear, obviously, everything above that up into the point of pain and beyond. So this is the decibel chart, right? Which, once again, I'm giving you sort of two definitions of decibels. I'm saying, decibel is a unit of measurement of sound. Okay, that makes sense. We're looking at the chart here. But I'm also saying that it's a relative unit of measurement in like a recording situation. In other words, if you put a mic on me and, you set your equipment so that that is 0 decibels, right? Whatever volume I'm coming in at, then you have the ability to turn that up or down, add 1 decibel, subtract 1 decibel, and you're increasing or decreasing the volume, right? Okay, so decibel, volume of sound. Now there's another phrase here, which is hertz. And of course, decibel is written D, lowercase d, uppercase b. Another term is hertz, written uppercase h and lowercase z. Does anybody know what hertz are? Or what hertz is a unit of measurement, but what's it used to measure?
It's used to measure frequency.
That's correct. So it measures the frequency of a sound. Now we talked about the fact that sounds have these sound waves, right? And we've seen examples of sound waves. So let's look at some images here. Okay, so these are sound waves, and every sound wave has a certain frequency. And frequency, of course, means how often something happens. Well, within what we call a cycle, a sound will repeat, a sound wave will repeat a certain amount of times. And the more times it repeats, the higher its frequency. So I'm always using the example of like a bass guitar or a human voice or violin or something like that. So, assuming, let's see if we have some different sound waves here we can use for example. So let's just say for the sake of argument that this is a sound wave that represents a human voice, my voice talking, right? A violin would have a lot more of these little sound waves happening within the same amount of time. In other words, it would occur more frequently. So it would have a higher frequency than my voice. So, if my voice is like 40 hertz, then a violin might be something like 60 or 120 hertz, right? It might be up there where that, the frequency is the sound waves are happening very frequently, and that's what produces that high, beautiful sound, right? Whereas a bass guitar has a lower frequency, so it might have something like 10 or 20 cycles, of frequency, 10 or 20 hertz. In other words, it doesn't repeat very often. It's just a really long, slow sound wave, and that's what its frequency is, right? Let's see if there's any other good examples here in this chart or in these pictures here. It looks like it's all just examples. Yeah, here we go. Here's a good one. So you see, here's a high. Let me see if I can get this a little bigger. No, it's very small. But a high frequency, high pitched sound over 1 second, and that's referred to as the cycle. How long you're measuring. You can see that this got 3 waves in a high pitched frequency sound like a violin. Whereas you have a low frequency, low pitched sound like a bass guitar. See how it's only getting like just this one, almost half a cycle here of a sound in 1 second, as opposed to 3 waves over here. So, and once again, here's another example: low frequency, medium frequency, and high frequency. Okay, so the more often we get the sound waves, the higher the frequency, the higher the sound. Okay, all right, so, and then the definition here: decibel is how loud a sound is. A hertz is the sound's frequency. How are they used? Decibels are used to measure the relative volume of a sound. Hertz are used to define a sound's frequency relative to other sounds. Okay.
Okay. One thing on the decibels, when you use it to do the absolute the sort of the different volumes of sound coming at you, a lot of people in the sort of OSHA type industries refer to that as dB/SPL, or sound pressure level.
Okay.
But when you're using it dB for recording on a meter, typically 0 dB is the limit of the equipment, and if you go above 0 dB, the recording starts to distort. So you want to keep your sound levels that you're inputting into your recorder less than 0 dB in order to avoid distortion, unless you want distortion.
That's an excellent point, and thanks for mentioning it. And I think what I would say is that that decibels are used in different ways based on the purpose. Like Bill just defined a couple, which is like, and he's right. If you have a sound meter like in Adobe Audition, it's going to show 0 dB right at the point where the red is going to when you have your green, your yellow, and your red. When you get up to 0 dB, you're going to be once you go hit that or above it, you're going to go into the red. In other words, it's going to start to distort. So they're using decibels in that sense to say, okay, we've said 0 is the limit you don't want to go to, so have a negative number that won't let you hit 0, right? That's one use of decibels. Don't get this loud at this 0 point, right? Another use is when you're recording and you're getting a certain volume and somebody says, "Oh, it's not loud enough. Can you turn that up a few more dB or decibels?" Then you can turn the knob a couple times and now you're getting more volume, right? And then a third function of it is to just, as we saw in the chart, register how loud things are in the physical world in dBs. So a quiet office is 40 and the threshold of pain is 120, right? So it's a unit of measurement that can be used in multiple ways. But thank you, Bill. You've got a lot of knowledge about that, and I appreciate it. And one of the terms that Bill used was SPL, which is sound pressure level, and that's basically measuring, you know, when you have a diaphragm on like a microphone, it gets hit by sound pressure, right? So when you speak, you create pressure from your voice that hits air molecules, that hit other molecules, and it goes out across the room until it hits the diaphragm of a microphone. Well, how hard it hits that is the sound pressure level. And a louder sound will hit the diaphragm harder and make it, vibrate more than a softer sound, which will have a lower SPL. So, as Bill said, decibels and sound pressure level are other, he says dBSPL. You can kind of combine those two and think of them as the same thing. Loudness and sound pressure are roughly equivalent. Okay, so it says define the following terms. Now, frequency, we talked about the fact that Hertz measures frequency, or how frequently, a sound wave occurs in a given cycle, right? So frequency is the rate at which a sound repeats within a given time period, like a cycle, like 1 second, right? Now, another term is in sound is amplitude. And amplitude refers, if you take a center line, you have a sound wave here and you put a center line through it. Amplitude is how high and how low the sound wave goes above that center line. That's referred to as the amplitude. So amplitude, the distance or above or below the center line of a waveform, right? Now every sound that is made, creates a sound wave, and that wave has what's called a wavelength, like how long the actual wave of the sound is as it travels through the air. Now this is kind of surprising, but bass guitar notes can have sound waves that are anywhere from 10 to 30 feet long, right? So you hit a low note on the bass, and that thing can travel for like, 10 to 30 feet, to make that entire wavelength, right? So that's a pretty incredibly long wavelength, whereas a very higher pitch instrument would have a much shorter wavelength. So it says the wavelength is the physical distance between the beginning and the end of the cycle of the wave, right? Now, the next term that we're going to define here is relative to the demonstration that I did last week, which is called phase. And last week we took two signals, and we took one and we played it, and then we took one which was completely the exact opposite of that. In other words, it was inverted, and we played it at the same time. And what it did was it canceled out the first sound. So if you have a sound wave, that has all of these, peaks going like this, and you copy that in Photoshop and you flipped it over, and so now the peaks were now valleys, and they exactly corresponded to the first wave, you would get this kind of phasing where basically one sound would cancel out the other, and you would get just the center line, which is zero, it's nothing, right? So that's what can happen, and phasing is not a good thing most of the time. It means you're losing signals because of dropouts, because of phasing. So it says whether a sound is being canceled out by an inverse version of the sound. Okay, and we're almost done here, and I know there's a lot of information, a lot of terms, but as I said, I just want this stuff to go by your ear and into your head, and hopefully with enough repetition and usage in this field, this stuff will start to make sense, or at least stick with you. So the next definition here is something called harmonic content, which can also be referred to as overtones or partials. And so what happens is when you make a sound, hold on, I've got a guitar right here. a guitar that I'm banging into a coffee table, but I don't know how in tune this is. It's relatively in tune, right? But when you make a sound, when you hit a specific guitar string, that's a very low one. Let me hit a higher one. Okay. When you hit a certain pitch, in this case it's E, the high string on a guitar, what happens is, especially on an instrument like a guitar, it's vibrating, at a very high frequency, and so it's sounding that note, right? However, because there's 5 other strings on the guitar, that vibration from that string is also slightly vibrating the other strings on the guitar, and each of them are producing little notes too, right? These notes are referred to as overtones or partials, right? You're hearing that sound, but you're also hearing some other vibrations, some harmonic content. Is one term that they use for it. It's what's being defined here. So in other words, if all music that was recorded was just that single sound, it would be very boring because it would just be like, very mechanical. This note, now this note, now this note, now this note. But because vibrations affect everything, when you do hit a sound and it vibrates, it causes vibrations and things around it and creates these overtones and these partials, right? And that is part of what gives sound, and especially music, its beauty, is all of those extra notes, right? And this is one of the reasons why when we talked about analog recording that was done to that's done to tape recorders, giant 2-inch tape reels, versus digital recording, which is recorded directly into a computer. This is why analog recording is sometimes considered a superior form of recording, because it captures all of those overtones. It gets all of the color and all the ambience of a sound. Now, digital recording, by its very nature, has to make choices. It has to say, okay, here's all the sounds, that are being recorded, but since I only have so much memory, and since the main sound is right here in the middle, I'll just compress the amount of sound that I capture, and I'll capture this little slice of sound out of the whole possible range of sounds that are being sounded. And so as a result, you get sort of a very clean, sterile, accurate digital sound, but it's not warm and it doesn't have these extra overtones that, produce all that color that we see as pleasing. Okay, so, and the last thing here is what we talked about earlier, which is, what is a sound envelope? And a sound envelope is a way to describe all of the aspects of a sound, right? Especially when you think of a synthesizer is a great way to define this. And so there's 4 aspects to sound in this description: attack, decay, sustain. Attack, decay, sustain, and release, right? So attack is, the time it takes for the sound to initially start. The decay is the time it takes for it to go from the sort of its peak down to what's going to be the sustain level of the sound. Of course, the sustain is the average, sound itself over time, and then the release is the sound sort of decaying, and going down to 0. So once again, that little chart that goes up, comes down a little bit, goes straight across, and then down again. That's really all you have to think about when you think about a sound envelope, is how sound is created and deployed in that manner. Okay, and that's it. Now, as I said, let me go back to the class website here. Boom. Oops. I don't know where the heck it's here. Okay. Here we go. Yeah. Did you have a question or?
One good way to illustrate wavelength
Mm-hmm.
is using the pipes of a pipe organ, because each pipe is the wavelength of the sound that it creates.
Oh, that's a great
Might
analogy.
be half depending on if it's capped, but open ones are the exact wavelength of the sound that it is going to create.
Okay, so in other words, a longer pipe would create a lower sound.
Yes.
Okay, so that's really clever, and that's a great way to think about it. So because pipe organs have all these different size pipes, the smaller pipes are going to produce higher sounds. The medium pipes will be medium, and then the long pipes will produce low sounds. And you can see by the way that they're created here that they're happening in intervals. Like here's, this might be like there might be an interval of a third between these two notes, and then a third again, a third again, and a third again. So it's how you produce pleasing music is these regular intervals that,
Yeah.
that give you the sounds that we think of as pleasing.
Yeah, they correspond to the exact keys on the keyboard.
Right, right, exactly. Yeah, it's fascinating. It's a good, wow, look at this one here. Is that insane? God, look at all those pipes. That is insane. Okay, yeah. So, all right, thank you, Bill. That's another good point. Okay, so once again, here on the website is a list of all of the basically quiz questions. And since it's open book, you guys can basically write down all the answers to these and turn them in on Wednesday if you like. I'll give you time on Wednesday to actually do it in class, and I'm going to give you some time today to actually do it in class too. It may be that all of you do it in advance and you just turn it in on Wednesday, and I'm fine with that. I have a file here that I can put up on the website. Let me see if I can open it real quick. Oh no, where'd it go? It should be in recent documents. Let's see. Let me hit open. There can't be that many things on my desktop that look like an ODF file, so let me find it real quick. Let's see, what would I call it? Probably, what's it called at the top here? Something like audio quiz or something like that. Yep, here it is. Audio quiz. Let me open that up. Okay, so this is the quiz itself. So I think what I'm going to do right now, I'm going to upload this to the website. You guys can download it, and I'm going to give you time right now to go ahead and do the research, write this stuff down, and basically do your quiz, and you can turn it in whenever you like. It's due on Wednesday. And then you can take the rest of the period to work on project 2, your Foley project, if you get this thing finished up. So let me go ahead and save this. I'll save this as a Microsoft Word document and put it on the website. So let's see, audio quiz, open book, and I'll call this MW or Microsoft Word and audio quiz. Okay, save that. Keep current format. Let me go ahead and put this, okay, whatever, edit this. And I'll just put a thing up here that says, here is the quiz, and link to that. Okay, audio. Where'd it go? It didn't save in the same place. Okay, let's go back. What? Requires a Java runtime environment to perform the police. What? Oh my God. Wow, that was not cool. It gave me some funky answer. Let me see if I can save it as a PDF, because hopefully that will work. All right, here it is. So we'll go, let's see, no cable. Okay, file, save, ignore. Okay, first let's try saving as a PDF. Open book, desktop, save. Okay, that worked, cool. All right, so now we'll go back here, audio quiz, open book, PDF, open. And then we'll get the link, copy that, and link it to that. Update. Okay, so that should be on the class website now. Let me click on it and make sure the link works. Okay, it looks like it does. All right, so yeah, why don't I give you guys some time right now? Basically, you have the rest of the period. Work on this, get all your, download this. You can fill out, you can use any kind of word processor and just answer these questions, and then upload that back to me, email that to me, and that will be your quiz. And then once you get that done, you can, and that's due Wednesday. And once you get that done, you can work on your Foley project. And we don't have a due date for that yet, but we'll check in with you on Wednesday and see how you're doing, what progress you've made. Any questions from you guys? Okay. All right. So go ahead and work on that. I'm gonna turn my video off, but I'll leave my audio on. If you have any questions, just pop in and ask me, and I'll check back in with you near the end of class. All right. Thank you.
Thanks, Greg.